Welcome to the Late Lab. It's wonderful to have you here. Before the night settles in completely, there's a gentle question to send out into the dark. Where are you watching from this evening? A dim room with the lights turned low, a quiet sofa under a blanket, a late bus ride home with the world sliding softly past the window? Wherever this finds you, may the next little while feel calm, safe, and easy to sink into. If these slow journeys through science help make the night a little softer, a like and subscribe is always deeply appreciated. It helps this quiet corner of the internet keep drifting along. And if you're already subscribed, thank you. Truly. Every bit of support helps more than it may seem. Now, tonight's subject is one of those ideas that sounds as if physics stayed up too late and began making suspiciously poetic decisions. So with any luck, it will be interesting enough to invite curiosity, but not so interesting that it leaves anyone staring at the ceiling at 3 a.m, wondering whether two particles on opposite sides of the universe are somehow still keeping in touch. Although, to be fair, there are worse thoughts to have at 3 a.m, so let's begin, quietly and carefully. What is quantum entanglement? And why does it seem to suggest that the universe is far less separate than it looks? There is a kind of connection in nature that refuses to behave like a connection at all. It is not a thread stretched through space. It is not a message travelling from one particle to another. It is not a tiny whisper moving faster than light, carrying secret instructions across the darkness. Quantum entanglement is stranger than those images, and also much more careful. It is not magic dressed in a laboratory coat. It is a real, tested feature of quantum mechanics, seen in experiments with photons, electrons, atoms, ions, and other controlled quantum systems. The mystery begins with a simple idea that does not stay simple for very long. Two particles can be prepared in such a way that they are no longer fully described as two independent things. Instead, quantum mechanics describes them with one shared quantum state. The particles may later move apart. They may be separated across a laboratory, across a city, or across much greater distances in specialized experiments. Yet the best description of them still belongs to the pair as a whole. That is where ordinary intuition begins to creak slightly, like an old chair being asked to support a grand piano. In everyday life, separation seems straightforward. A cup on one side of a room and a spoon on the other side are separate objects. Ordinary objects usually carry their own properties with them. A coin is heads or tails. A glove is left-handed or right-handed. A sealed envelope contains whatever was placed inside it before it was sealed. These examples can help at first. Imagine a pair of gloves placed into two boxes. One box is sent to London, the other to Sydney. If the London box is opened and contains the left glove, the Sydney box must contain the right glove. The knowledge appears instantly, but nothing physically strange has happened. No signal has crossed the planet. The gloves had their handedness from the beginning, and opening one box simply revealed what was already true. Entanglement is tempting to explain in that way. Perhaps two particles are simply like those gloves. Perhaps they carry fixed instructions from the moment they are created, and measurement merely reveals the answer. That would be comfortable. It would keep the universe tidy. It would let common sense sit back down with a biscuit and feel it had done a decent job. But quantum mechanics does not allow the glove example to survive unchanged. When entangled particles are measured in different carefully chosen ways, the patterns in the results are not the patterns expected from ordinary hidden instructions. The outcomes are correlated, but not merely in the way two objects are correlated because they were packed together earlier. Quantum mechanics predicts stronger and more subtle relationships than classical pictures allow, and experiments have repeatedly supported those predictions. This is why entanglement deserves its reputation as the strangest connection in the universe. The strangeness is not simply that two particles can be linked. Many things are linked. The strangeness is that the link challenges the usual assumption that every object carries its own complete set of properties before anyone checks. In an entangled system, the full description belongs to the combined system, not neatly to each particle separately. This does not mean that entanglement allows telepathy. It does not mean that particles are conscious. It does not mean the universe is sending messages in tiny glowing envelopes, although that would at least be very organized of it. Entanglement cannot be used to send information faster than light. A person measuring one particle cannot choose the outcome and use it to control what happens far away. The results only reveal their special pattern when both sides are later compared through ordinary communication. So the real mystery is quieter than the popular version, but deeper. Entanglement does not break physics by turning particles into magical messengers. It reveals that the ordinary idea of separateness is incomplete at the quantum level. Two things can be apart in space while still belonging to one shared quantum description. This idea grew from the strange revolution in physics that unfolded during the early 20th century. Max Planck showed that energy could come in discrete packets while studying radiation from hot objects. Albert Einstein used light quanta to explain the photoelectric effect, helping establish that light can behave as particle-like units called photons. Niels Bohr proposed a quantum model of the atom where electrons occupy allowed states. Werner Heisenberg developed matrix mechanics and the uncertainty principle. Erwin Schrödinger introduced wave mechanics. Paul Dirac helped connect quantum mechanics with special relativity and predicted antimatter. These names can sound like statues in the Grand Museum of Physics, but they were dealing with a practical problem. Nature was not behaving like a miniature version of the everyday world. Atoms, light, and electrons were not tiny billiard balls. They followed rules that were precise, repeatable, and deeply unfamiliar. Quantum mechanics became the framework that made sense of those rules. Entanglement emerged from that framework as one of its most unsettling consequences. It suggested that the world at its smallest scales cannot always be understood as a collection of separate objects carrying fixed properties in advance. Sometimes the relationship is part of the physical description itself. Sometimes the whole cannot be reduced to the parts in the comfortable way common sense expects. This was the issue that troubled Einstein. He was not afraid of strange ideas. He had already reshaped the meaning of space and time, but he disliked the suggestion that quantum mechanics might be complete if it gave up definite properties before measurement. Niels Bohr accepted the quantum framework more fully, and their disagreement became one of the great debates in modern science. Then John Stuart Bell showed that the debate could be tested. Bell's theorem revealed that certain hidden instruction explanations must obey statistical limits. Quantum mechanics predicted that entangled particles could go beyond those limits, and later experiments showed that nature follows the quantum prediction. Entanglement is not a metaphor. It is a measured feature of reality, one that now sits at the heart of quantum information, quantum communication, and quantum computing. It begins with a simple question. Can two distant things still belong together? The answer from quantum physics is careful, limited, and astonishing. In some cases, yes, but not in any ordinary way. And so the connection that should not be simple becomes a doorway. Through it, reality stops looking like isolated pieces and starts looking more like a pattern of relationships, some visible, some hidden, and so delicate that they only appear when the universe is asked the question in exactly the right way. Ordinary connections are everywhere, and most of them are so familiar that they barely ask to be noticed. A hand pushes a door and the door opens. A spoon taps the side of a mug and the mug rings gently. One billiard ball rolls across a table, touches another, and sends it gliding away with a small clack that sounds like physics politely clearing its throat. These are connections by contact. Something touches something else, Motion is passed along. A cause has a root, and the route can be followed. Other connections work without direct touch, but they still behave in ways that make sense. A radio antenna sends an electromagnetic wave through space, and a receiver picks it up later. A phone call crosses networks of cables, fiber optics, towers, satellites, and electronic systems. A lighthouse sends light across water. The message is not everywhere at once. It travels. It takes time. It can be blocked, delayed, weakened, reflected, or lost completely if the universe is feeling slightly inconvenient. Even time can be connected in an ordinary way. Two clocks can be synchronized, then carried to separate places. If they are well made and treated carefully, they may continue to agree. Their agreement is not mysterious. It comes from preparation. Someone set them together. They share a history. If they later show the same time, it does not mean one clock is secretly controlling the other from across the room. It means they were arranged to match. This kind of shared history is the heart of ordinary correlation. Two things can be linked because of something that happened earlier. A pair of shoes comes from the same box. Two halves of a torn photograph fit together because they were once part of the same image. A matching set of keys opens the same lock because someone cut them that way. The relationship may be useful, but it is not shocking. It is the quiet bookkeeping of the everyday world. A classic example is the pair of gloves. Imagine two gloves, one left and one right, placed into two sealed boxes. One box is sent to London, and the other is sent to Sydney. Before either box is opened, the person in London does not know which glove they have. It could be the left glove, or it could be the right glove. But the situation itself is not undecided. The gloves already have their handedness. The boxes simply hide the answer. When the London box is opened and the left glove is found inside, the person in London instantly knows that the Sydney box contains the right glove. This knowledge appears immediately, but nothing physical has raced across the planet. No signal has flashed through Earth. No strange force has tugged on wool, leather, or whatever unfortunate material the gloves are made of. The connection was created in the past when the gloves were packed. Opening one box only reveals part of an already settled arrangement. This is the kind of explanation the mind naturally reaches for when first hearing about quantum entanglement. It feels sensible. If two particles are created together, then separated, perhaps they are just carrying matching instructions. Perhaps one particle has one answer, and the other particle has the corresponding answer. Perhaps measurement simply opens the box. For much of ordinary life, that kind of reasoning works beautifully. Classical physics is built around a world in which objects have definite properties, whether anyone is observing them or not. In Isaac Newton's mechanics, a planet has a position, a speed, and a mass. A stone follows a path through the air. A falling apple does not wait politely for an observer before deciding whether gravity applies today. Gravity, thankfully, is not that theatrical. James Clerk Maxwell's theory of electromagnetism added fields to the picture, showing that electricity, magnetism, and light are deeply connected. Even so, the classical world remained one in which physical quantities were usually treated as definite. Electric fields, magnetic fields, waves, charges, and moving objects could be described by values that existed as part of the physical situation. Measurement might disturb a delicate system in practice, but the property being measured was still usually imagined as something already there. Albert Einstein made the picture deeper and stranger with special relativity and general relativity. Space and time were no longer fixed backgrounds in the old Newtonian sense. Gravity became the curvature of space-time. Clocks could tick at different rates depending on motion and gravity. Yet even in relativity, the universe remains strongly committed to locality. Causes do not simply leap across space with no physical route. Usable signals do not outrun light. Events are woven into space-time with a structure that decides what can influence what. So the classical instinct is powerful. It says that if two separated things show related results, the explanation should be contact, a signal, a shared past, or hidden information carried from the beginning. That instinct is not foolish. It is one of the reasons science works. It asks for mechanisms instead of miracles. It refuses to be impressed by mystery until the mystery has earned its shoes. Quantum entanglement begins by looking as if it might fit inside this familiar picture. Two particles are prepared together. Later, they are separated. Then, when scientists measure them, the results are correlated. At first glance, this sounds exactly like the glove boxes. One result tells something about the other, because both particles must have carried related properties all along. But this is where ordinary connection begins to fall apart. The difference is not just that the particles are small. It is not simply that quantum objects are difficult to measure. The deeper difference is that quantum mechanics does not describe entangled particles as two separate objects with two separate private lists of answers. It describes them with one shared quantum state. The state belongs to the combined system. In many cases, it cannot be broken down into a complete state for one particle and a complete state for the other. That is already unfamiliar, but the real trouble appears when different measurements can be chosen after the particles have separated. With gloves, there is only one simple question, left or right. But in quantum experiments, scientists can choose between different measurement settings. For example, with entangled photons, they may measure polarization along different angles. With particles involving spin, they may choose different directions of measurement. Quantum mechanics predicts how the results should be correlated across many repeated trials. If the particles merely carried fixed hidden instructions, those instructions would need to account for all the possible measurement choices. The particles would, in effect, have to arrive with a full rulebook already packed inside them. That sounds possible at first. It sounds like the universe being extremely organized, which would be a pleasant surprise given the average state of most kitchen drawers. Yet quantum experiments show correlations that do not match the limits expected from ordinary local hidden instruction models. The pattern is not just strong. It is strong in a specifically quantum way. It agrees with the mathematics of entangled states, not with the simple idea that each particle carried a complete set of pre-written answers from the start. This is why entanglement is not merely ordinary correlation with a dramatic name. Classical correlation comes from shared history or direct influence. Quantum correlation, in entanglement, comes from the structure of the shared quantum state itself. The particles are not just two distant objects that happen to resemble each other. They are parts of one physical description that produces measurement patterns no classical glove box can reproduce. The strange reputation of entanglement comes from this quiet escape. It begins close to familiar ideas. It borrows the shape of ordinary connection just long enough to seem understandable. Then, when the measurements become more careful, it slips beyond the old categories. It is not contact. It is not a signal. It is not merely hidden information in the usual sense. It is a connection that resembles the everyday world only from a distance, like a lighthouse that turns out on closer inspection to be a star. To understand why entanglement is so difficult to squeeze into ordinary ideas, it helps to meet one of the central objects in quantum mechanics, the quantum state. The phrase can sound cold and mathematical, as if it belongs on a chalkboard in a room where everyone has already agreed not to make eye contact. But the idea behind it is not there to make physics feel distant. A quantum state is the description physicists use when they want to predict what can happen when a quantum system is measured. It does not usually say, in a simple classical way, this particle definitely has this exact property right now, whether anyone checks or not. Instead, it contains the information needed to calculate the possible results of future measurements and how likely those results are to appear. That difference is subtle, but it matters enormously. In classical physics, a state is usually quite straightforward. If a ball is moving through the air, its state might include where it is, how fast it is moving, and in what direction. If those details are known precisely enough, and the forces acting on the ball are known, then its future motion can be predicted. In practice, there may be air, resistance, spin, wind, measurement errors, and the deeply unpredictable behaviour of anyone trying to catch it. But the basic idea remains clear. The ball has position and velocity. The description is meant to reflect properties the ball actually has. A quantum state is not quite like that. It is not simply a tiny object carrying a hidden list of ordinary properties. It is a mathematical description that tells physicists what kinds of answers nature may give when a measurement is performed. For an electron, it may describe possible outcomes for position, momentum, spin, or energy. For a photon, it may describe possible outcomes for polarization, path, or energy. The state is not a little label attached to the particle saying exactly what will be found in every possible experiment. It is more like a compact rulebook for probabilities, although even that comparison has to be handled gently, because quantum rulebooks have a habit of being far more interesting than ordinary rulebooks, and much less willing to sit quietly on a shelf. One of the most famous ways of representing a quantum state is the wave function, associated with Erwin Schrödinger. Schrödinger developed wave mechanics in the 1920s, giving quantum theory a form that described particles through wave-like mathematical objects. This did not mean that an electron was simply a tiny ocean wave, sloshing around inside the atom with a little microscopic surfboard nearby. It meant that the behaviour of quantum systems could be described using wave-like mathematics, including interference, spreading, and probabilities. The wave function became one of the great symbols of quantum mechanics because it captured something deeply unfamiliar. Before measurement, quantum systems are often described not as having one definite value for a property, but as being in a state that can lead to different possible outcomes. This is where superposition enters the story. Superposition means that a quantum system can be described as a combination of possible measurement outcomes before a particular measurement is made. A photon's polarization, for example, may not be simply fixed as one definite answer for every possible measuring angle. An electron's spin may not be neatly pre-written as one ordinary direction for every kind of spin measurement. An atom's electron may occupy an energy state described by quantum rules, and in some situations a quantum system may be prepared in a combination of possible energy states. This can sound as if quantum mechanics is saying a particle is magically anything anyone imagines it to be. It is not. Superposition is not a cosmic permission slip for vagueness. It is precise. Quantum theory does not say, anything can happen, good luck. It assigns specific probabilities to specific possible outcomes. The possibilities are not random fantasies. They are constrained by the quantum state, by the way the system was prepared, and by the kind of measurement being performed. A useful way to think about this is to remember that quantum mechanics is astonishingly good at prediction. It underlies modern chemistry, lasers, semiconductors, magnetic resonance imaging, atomic clocks, and the physics of materials. If it were simply a poetic way of saying who knows, it would not have survived very long outside a philosophy seminar with comfortable chairs. It works because its probability rules are mathematically exact and experimentally reliable. The key question is what those probabilities mean. This is where Max Born becomes important. In 1926, Bohr proposed the rule connecting the wave function to measurement probabilities. The Bohr rule says, in plain language, that the quantum state can be used to calculate the likelihood of different measurement results. It does not usually claim that all those results were already sitting inside the particle like folded notes in a pocket. It tells physicists how to predict the statistical pattern that appears when many identically prepared systems are measured. That may sound modest, but it was a profound shift. In classical thinking, probability often reflects ignorance. A coin under a cup is already heads or tails. Not knowing which one does not mean the coin itself is undecided. The probability belongs to the observer's lack of information. In quantum mechanics, the situation is more delicate. The probabilities often seem to be built into the physical description itself, not merely into human ignorance about a hidden answer. Measurement then becomes one of the defining issues in quantum theory. A quantum state may contain several possible outcomes with assigned probabilities, but a measuring device records one actual result. A detector clicks. A screen shows a spot. An atom is found in one energy state rather than another. The world of possibility narrows into an event. Quantum mechanics gives a powerful recipe for predicting the statistics of those events, but the deeper meaning of measurement remains one of the places where interpretation begins to matter. This is already strange for a single particle. A lone photon or electron can have a quantum state that does not resemble a classical object with a complete list of definite properties waiting to be revealed. But entanglement takes this strangeness and gives it company. If one particle can be described by a quantum state that predicts possible outcomes rather than simply listing hidden properties, then two particles can be described by a combined quantum state. And in some cases, that combined state cannot be separated into one complete state for the first particle and another complete state for the second. The whole description belongs to the pair. This is the step where entanglement begins to emerge naturally. It is not added to quantum mechanics as an extra mystery for decoration, like a strange hat on an already unusual statue. It grows from the basic structure of the theory. Quantum states can describe individual systems, but they can also describe combined systems. And when the combined description cannot be reduced to the separate descriptions of the parts, the particles are entangled. So the quantum state is the doorway. It changes the question from what properties are hidden inside this particle to what does the full quantum description allow us to predict when we measure. Once that shift is made, entanglement becomes less like a magic trick and more like a consequence of the rules. The rules are unfamiliar, certainly. They are not the rules of gloves, coins, clocks, or billiard balls, but they are not vague. They are careful, mathematical, and repeatedly tested. The universe at this scale seems less interested in providing tiny objects with private answer sheets and more interested in giving systems a shared structure of possibilities. And sometimes that shared structure reaches across more than one particle, making the connection between them deeper than ordinary separateness would ever suggest. Quantum entanglement begins when the best description of two particles no longer belongs neatly to either particle alone. That is the simplest way to say it, though simple does not necessarily mean comfortable. In ordinary thinking, if there are two objects, there should be two separate descriptions. One description for the first object, one description for the second. A coin in one hand, a coin in another, a stone here, a stone there. A small sandwich on one plate, a suspiciously missing sandwich on another. The world appears to be made of separate things, each carrying its own facts. But in quantum mechanics, two particles can sometimes be described by one combined quantum state. The full state belongs to the pair. It cannot always be split into a complete state for one particle and a complete state for the other. The particles may later be separated, but the quantum description still treats them as parts of one system. This is the central idea of entanglement. Entanglement can arise in several ways. Particles can become entangled when they interact with each other, because interaction allows their properties to become linked within a shared quantum description. Two atoms might interact through electromagnetic forces. Two particles might scatter from one another. A controlled laboratory system might be prepared so that the possible outcomes for one part are tied to the possible outcomes for another. Entanglement can also appear when one parent particle or quantum system produces two related products. If a particle decays into two other particles, conservation laws can connect their properties. Conservation laws are among the deepest bookkeeping rules in physics. They say that certain quantities, such as energy, momentum, electric charge, and angular momentum, must remain balanced before and after an interaction. The universe may be strange, but it is not usually careless with its accounts. For example, if a parent system begins with a certain total angular momentum, then the particles produced from it must share outcomes that preserve that total. Angular momentum is a property associated with rotation and orientation in physical systems, though in quantum mechanics it appears in forms that are not always easy to picture. This shared constraint can help produce linked measurement results. The particles are not simply random fragments flying away, with no memory of how they were created. Their possible properties are connected by the structure of the original event. One of the clearest examples used in entanglement experiments involves photons, the particle-like packets of light. Photons can be entangled in their polarization. Polarization describes the orientation of light's electric field as the light travels. In ordinary terms, light is an electromagnetic wave, and its electric field can oscillate in different directions. A polarizing filter, such as the kind used in some sunglasses, can allow certain orientations of light through while blocking others. In laboratories, entangled photons are often produced using a process called spontaneous parametric down conversion. In this process, a photon enters a special nonlinear crystal and can be converted into two lower energy photons whose properties are linked. The details involve careful optical equipment, precise alignment, and enough delicate apparatus to make anyone near the table instinctively walk more slowly. But the basic idea is that one incoming photon can give rise to a pair of photons whose polarization states are described together. These photon pairs are useful because polarization can be measured at different angles. Physicists can send the two photons in different directions, measure each one separately, and then compare the results. What matters is not just that the results show some connection. Ordinary shared history could do that. What matters is the particular statistical pattern produced across many repeated trials. Quantum mechanics predicts correlations that go beyond what a broad class of local hidden variable explanations can reproduce. Another important example involves electron spin. The word spin is slightly misleading, because an electron is not literally a tiny planet rotating on its axis. It is not a miniature tennis ball, which is probably for the best, because the subatomic world has enough difficulties already. Spin is an intrinsic quantum property. It behaves mathematically like a form of angular momentum, and it can be measured along different directions. When two particles are entangled in spin, measuring the spin of one particle can reveal a correlation with the spin measured on the other. The strangeness is not merely that one result is related to another. Related results are everywhere in physics. If two skaters push away from each other on ice, their motions are linked by conservation of momentum. If one object breaks into two pieces, the paths of the pieces can reveal something about the original object. Shared origin can explain many correlations perfectly well. Entanglement becomes strange because quantum theory predicts correlations that do not fit the idea that each particle simply carried a full set of fixed answers from the start, at least not within ordinary local hidden variable models. The particles behave as though the combined state is the physically meaningful object, even when the parts are measured separately. The relationship is not a decorative extra. It is built into the quantum description. This is why entanglement is sometimes described as two particles becoming one system. They do not merge into one object in the everyday sense. They do not stick together like droplets of water. They do not become connected by a tiny invisible rod. Each particle can still travel along its own path and arrive at its own detector. But the state that predicts their measurement outcomes belongs to the pair, and that shared state can produce correlations that ordinary separable descriptions cannot match. It is important to keep this grounded. Entanglement is real, but it is also fragile. In carefully controlled experiments, physicists work hard to isolate quantum systems from the surrounding environment. Stray light, air molecules, heat, vibrations, imperfect detectors, and unwanted interactions can all disturb the delicate quantum relationship. A quantum state that begins clean and entangled can quickly become tangled with the wider world in a much messier way, making the original entanglement difficult or impossible to use. This fragility is one reason entanglement does not usually appear in ordinary life. The world around us is warm, noisy, crowded, and constantly interacting with itself. Tables, cups, walls, air, dust, and human beings are not gently isolated quantum systems floating in perfect silence. They are more like extremely busy committee meetings made of atoms, and most committee meetings are not famous for preserving delicate clarity. Still, under the right conditions, entanglement can be prepared, measured, and used. It appears in experiments with photons, ions, atoms, superconducting circuits, and other quantum systems. It has become central to quantum information science, quantum communication, and attempts to build quantum computers. At its heart, entanglement shows that the smallest parts of nature do not always behave as separate little objects with private answer sheets. Sometimes the more accurate description belongs to the whole. Two particles can move apart, yet remain joined by a shared quantum state. Not by magic, not by a signal, and not by a hidden thread through space, but by the deeper structure of quantum mechanics itself. Albert Einstein is sometimes described as if he simply disliked quantum mechanics because it was strange. That picture is too small and not really fair to him. Einstein was not a man frightened by strangeness. He had already helped overturn comfortable ideas about space, time, light, gravity, and motion. In 1905, his special theory of relativity showed that space and time are not fixed in the old Newtonian way, and that the speed of light acts as a cosmic speed limit for usable signals. In 1915, his general theory of relativity described gravity not as an invisible pulling force in the old sense, but as the curvature of space-time itself. This was not exactly the work of someone who needed the universe to remain cozy and familiar. So when Einstein became uneasy about quantum mechanics, it was not because he could not tolerate weirdness. It was because he cared deeply about what a physical theory was supposed to mean. Quantum mechanics worked astonishingly well. By the early 20th century, it was explaining the behavior of atoms, light, radiation, chemical bonds, and the structure of matter with a precision classical physics could not match. Max Planck, Niels Bohr, Werner Heisenberg, Erwin Schrödinger, Max Born, Paul Dirac, and others had helped build a new framework for the microscopic world. The results were powerful, repeatable, and often extremely successful. Unfortunately for anyone hoping for a peaceful intellectual afternoon, they were also deeply unsettling. Einstein's concern centered on two ideas that seem very natural in ordinary life: locality and realism. Locality is the principle that physical influences do not simply leap across space instantly. If one thing affects another, that effect should travel by some physical process, and it should not outrun light. This mattered enormously to Einstein because special relativity placed the speed of light at the heart of causality. Signals, causes, and usable information are not supposed to move faster than light through space. The universe may be strange, but it should not allow events to nudge distant events instantly with no physical route between them. Realism is the idea that physical properties exist independently of whether someone observes them. A moon is not supposed to vanish into possibility when no one looks at it. A stone has a mass. A planet follows a path. A field has a value. Even if measurements are difficult and even if observers make mistakes, there is still meant to be a real physical situation underneath the act of observation. Einstein did not think physics should be only a catalogue of measurement results. He wanted a theory to describe what exists, not merely what can be predicted when instruments are used. To him, a complete theory should say something about reality itself. It should not stop too early and declare the deeper question unaskable, just because the mathematics gives excellent answers. Niels Bohr took a different view. Bohr, one of the central figures in the development of quantum theory, became closely associated with the Copenhagen interpretation. This interpretation is not one single perfectly fixed doctrine, but it is generally linked to the idea that quantum mechanics is not simply revealing hidden definite properties that particles possessed all along. Instead, it gives rules for what can be observed and predicted under particular experimental arrangements. For Bohr, the details of the measuring setup mattered profoundly. It was not enough to ask what a particle was doing in isolation, as if it carried a complete set of classical properties waiting to be inspected. In quantum mechanics, the kind of question asked by the experiment helps define the kind of answer that can appear. A measurement of position is not the same as a measurement of momentum. A measurement of photon polarization at one angle is not the same as a measurement at another angle. The physical arrangement is part of the meaning of the result. This was one of the deepest tensions between Einstein and Bohr. Einstein wanted quantum mechanics to point toward an underlying reality with definite properties. Bohr argued that quantum mechanics was already complete in its own terms, and that demanding hidden classical pictures behind it might be asking nature to behave like a familiar machine when it simply does not. Entanglement made this disagreement sharper. When two particles are entangled, quantum mechanics describes them with one shared state. If they're later separated and measured, the outcomes can show strong correlations. At first, that might sound harmless. Perhaps the particles simply carried matching hidden instructions from the beginning. But quantum theory suggested that the situation was not so ordinary. The results seemed to depend on a shared description that did not split neatly into independent properties for each distant particle. Einstein found this deeply troubling, because it appeared to place pressure on locality and realism at the same time. If measuring one particle allowed a prediction about another distant particle, then what exactly was happening? Did the distant particle already have the property before measurement? If so, perhaps quantum mechanics was incomplete, because it had failed to describe that hidden property. But if the distant property was not already definite, then measurement here seems somehow tied to what could be said about a system over there. This concern is often remembered through the phrase spooky action at a distance. It is a vivid phrase, and probably one of the few times in physics where the ghost story writes itself. But it can be misleading if it's taken too literally. Einstein was not claiming that quantum mechanics had discovered little ghostly signals zooming through space. His worry was more precise. He believed that a complete physical theory should not require distant events to be connected in a way that seemed to violate ordinary causal structure. The real question was whether quantum mechanics was complete. If quantum mechanics was complete, then the shared quantum state of entangled particles was not just a temporary placeholder for missing knowledge. It was the best possible description. The individual properties measured later were not simply hidden in the particles like notes tucked into sealed envelopes. Instead, the theory described a deeper relationship between possible outcomes. If quantum mechanics was incomplete, then perhaps there were hidden variables beneath it. These hidden variables would be unknown features of reality that determine measurement outcomes while preserving a more familiar picture of locality and definite properties. In that view, quantum probabilities might reflect human ignorance, rather than true indeterminacy in nature. The universe would still be strange, but perhaps not quite as strange as Bohr's view seemed to allow. Einstein's unease was therefore not a failure of imagination, it was a demand for clarity. He wanted to know whether quantum mechanics was describing the world, or only describing what observers could say about the world after measurement. That distinction may sound delicate, but it reaches into the centre of physics. Entanglement disturbed him, because it made separation look less simple than relativity and classical realism seemed to require. Two particles could be far apart, with no time for an ordinary signal to pass between them, and yet the quantum description still treated them as one combined system. The connection was not a wire, not a force in the usual sense, and not a message. It was something stranger, a relationship built into the state itself. And that was Einstein's uneasy question. Was quantum mechanics revealing that reality is genuinely non-classical at its roots, or was it merely an incomplete map hiding a deeper, more orderly territory underneath? The question was calm, precise, and profound. It asked whether the strangest connection in the universe was a final feature of nature, or a clue that another layer of nature still remained unseen. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published one of the most famous challenges in the history of quantum mechanics. The paper was not long, but its question was enormous. It asked whether the quantum mechanical description of physical reality could be considered complete. In other words, did quantum mechanics tell the whole story about nature, or was it an astonishingly successful theory that still left something deeper out? Today, the argument is usually called the EPR argument, after Einstein, Podolsky, and Rosen. Its aim was not to prove that quantum mechanics failed experimentally. By then, quantum theory had already shown remarkable power. It explained atoms, light, radiation, chemical behavior, and many features of the microscopic world that classical physics could not handle. The concern was not whether quantum mechanics worked. It clearly worked. The concern was what its success meant. Einstein, Podolsky, and Rosen focused on a situation involving two systems that had once interacted and then moved apart. Quantum mechanics could describe the pair with a shared state. That shared state allowed a physicist to make predictions about one system after measuring the other, even if the two systems were now far apart. To Einstein and his colleagues, this raised a serious problem. Their reasoning can be understood gently, without needing to climb into the full mathematics. Imagine two quantum systems that are linked by a shared history. They separate. One travels one way, the other travels another. If a measurement is made on the first system, quantum mechanics may allow a prediction about what would be found if the second system were measured in a corresponding way. The second system could be very far away, too far for any ordinary signal to pass between them in time. Now comes the unease. If measuring the first system lets someone predict something about the second system without disturbing it, then perhaps that property of the second system was already real before anyone measured it. If it was already real, then quantum mechanics seems incomplete, because the theory did not assign that definite property to the second system beforehand. It only gave the shared quantum description and the probabilities. This was the heart of the EPR challenge. The argument tried to show that quantum mechanics, if taken as complete, produced a strange tension with a reasonable-sounding idea of physical reality. If one can predict a property with certainty without disturbing the system, then that property seems to correspond to something real, and if quantum mechanics does not include that real property in its description, then perhaps quantum mechanics is missing something. This idea is closely tied to local realism. Locality is the principle that physical influences should not travel faster than light. It says that an event in one place should not instantly cause a physical change in another distant place, without a signal or influence crossing the space between them. This principle fitted naturally with Einstein's special theory of relativity, where the speed of light is the limit for usable signals and causal influence. Realism is the idea that physical properties exist independently of measurement. A system should have definite features whether or not someone is looking. The moon is not expected to wait for a telescope before becoming real. A particle, in this view, should not need a measuring device before having the property that measurement later reveals. Local realism combines these two instincts. It says that distant systems have their own real properties, and that one system cannot be instantly affected by a measurement performed far away. To Einstein, this was not narrow-mindedness. It was a sober demand that physics describe a world with clear physical causes and independently existing facts. Niels Bohr responded quickly, and his reply was famously subtle. Subtle, in this case, is a polite word physicists sometimes use when everyone agrees that the idea is important, but would also rather not explain it after dinner. Bohr did not accept the EPR conclusion that quantum mechanics was incomplete. He argued that the meaning of a quantum property could not be separated from the full experimental arrangement used to define and measure it. For Bohr, the issue was not that a signal was mechanically travelling from one particle to another. He did not think entanglement should be imagined as a little message darting through space. Instead, he believed the EPR argument misunderstood what quantum mechanics was saying about physical description. In quantum theory, the conditions of measurement are not merely passive details. They help define what can meaningfully be said about the system. This was a very different way of thinking. Einstein wanted a description of reality that existed clearly behind all possible measurements. Bohr insisted that quantum mechanics was complete, because it correctly described the possible outcomes of experiments as defined by actual measuring arrangements. The disagreement was not about a small technical detail. It was about what a physical theory is supposed to provide. The EPR argument made entanglement impossible to ignore. Before this, the strange features of quantum mechanics could sometimes be treated as puzzles about individual particles, atoms, or waves. But EPR showed that the theory seemed to say something unsettling about separated systems. Two distant parts of the universe could be described together in a way that did not fit comfortably with the old idea of independent local properties. It's important not to rush too quickly to the conclusion that Einstein was simply wrong. His challenge was not foolish. It was powerful because it sharpened the question. It forced physicists to ask whether the quantum state was a complete description of reality, or whether it was only a useful tool hiding deeper variables beneath it. It also forced them to separate different ideas that had often been blended together: prediction, measurement, disturbance, locality, realism, and completeness. For many years, the debate remained partly philosophical. Quantum mechanics kept succeeding. Experiments kept agreeing with its predictions. Lasers, semiconductors, atomic physics, and nuclear physics all grew from quantum principles. The practical success of the theory was not in doubt, yet the EPR question stayed alive, waiting quietly in the foundations. Was the shared quantum state merely a sign of missing information? Were entangled particles carrying hidden instructions from their shared past? Or was quantum mechanics revealing something genuinely non-classical about reality itself? The remarkable turn came later when John Stuart Bell found a way to move the question out of the realm of interpretation and into the laboratory. Bell showed that certain hidden variable explanations were not just philosophical alternatives. They made testable predictions. If the world obeyed local realism in the EPR sense, then measurement results should follow certain statistical limits. If quantum mechanics was right, those limits could be broken. The EPR challenge did not end the argument. It gave the argument its proper shape. It turned entanglement from an odd feature of quantum mathematics into one of the deepest questions physics had ever asked about reality, distance, and what it means for two things to be separate. For many years, the argument about entanglement seemed to hover in a misty region between physics and philosophy. Quantum mechanics worked. That much was hard to deny. It explained the behavior of atoms, predicted the properties of light and matter, and became one of the most successful scientific frameworks ever built. Yet the unease raised by Albert Einstein, Boris Podolsky, and Nathan Rosen did not disappear. It remained there, quietly asking whether quantum mechanics was truly complete, or whether deeper hidden facts lay beneath the theory like machinery under a polished floor. Then, in 1964, John Stuart Bell changed the shape of the problem. Bell was a physicist from Northern Ireland, and his great achievement was to take a question that seemed almost impossible to test and give it experimental teeth. The debate had sounded like a disagreement about interpretation. Einstein wanted a world in which distant things possessed their own definite properties and in which no physical influence travelled faster than light. Niels Bohr and other defenders of standard quantum mechanics accepted that the quantum state did not behave like a hidden catalogue of pre-existing answers. For a long time, it was tempting to think both sides were simply choosing different ways to talk about the same experimental facts. Bell showed that this was not quite true. His theorem revealed that a broad class of hidden variable theories must obey certain statistical limits. Hidden variables are hypothetical, deeper facts that would determine the outcomes of quantum measurements beneath the ordinary quantum description. In a hidden variable picture, quantum randomness might not be fundamental. It might only look random because something is missing from the theory. The particle might carry more information than quantum mechanics describes, rather like a sealed envelope carrying instructions that nobody has opened yet. This idea sounds natural because it resembles ordinary life. If a coin is hidden under a cup, the coin is already heads or tails. Not knowing the answer does not make the coin undecided. The uncertainty belongs to the observer, not to the coin. A hidden variable theory tries to give quantum mechanics something like that deeper certainty. It asks whether quantum probabilities are really signs of ignorance about underlying facts. But Bell did not examine every possible hidden variable idea. He focused on hidden variable theories that also respect locality. Locality says that what happens in one place cannot instantly control what happens in a distant place through a usable physical influence travelling faster than light. This was the kind of picture Einstein hoped could preserve a more familiar understanding of reality. Bell's theorem showed that if particles carry local hidden instructions, then their measurement results cannot be correlated beyond certain limits. These limits are now called Bell inequalities. A Bell inequality can be understood as a statistical boundary. It is not a wall made of brick or a law carved into stone by a very serious cosmic accountant, though that image has a certain charm. It is a mathematical limit on how strongly the results of distant measurements can match or mismatch if those results are produced by local hidden variables. If each particle carries its own instructions, and if no faster than light influence passes between the measurement devices, then the patterns in the results must stay within Bell's boundary. The brilliance of Bell's work was that this boundary could be checked. Imagine many pairs of entangled particles being created and sent in opposite directions. At each side, an experimenter can choose how to measure the particle. The important detail is that there is not just one fixed measurement. There are different possible measurement settings. With photons, for example, the measurement might involve polarization at different angles. With spin, it might involve choosing different directions along which to measure. Each individual result may look random, but when many results are compared, patterns appear. If the particles are carrying ordinary local hidden instructions, those patterns must obey Bell inequalities. If quantum mechanics is right, certain entangled states should produce correlations that violate those inequalities. In plain language, the connection between the outcomes should be too strong, too carefully patterned, to be explained by the particles simply carrying separate pre-written answer sheets from the moment they were created. This is the turning point. Bell gave physicists a way to ask nature directly. The answer predicted by quantum mechanics was unsettling. Entangled particles should sometimes produce correlations stronger than local hidden variable theories allow, not because one particle sends a controllable message to the other, not because information can be used to outrun light, but because the shared quantum state does not behave like two separate packets of hidden instructions. The combined system carries a structure that classical separability cannot reproduce. This distinction is important. Bell's theorem does not simply say that information travels faster than light. That is the tempting shortcut, and it is also the shortcut that leads directly into confusion, usually wearing a hat labelled spooky and waving enthusiastically from the wrong platform. Entanglement does not let someone choose an outcome on one side and send a message to the other side. Each local result still appears random, only when the two sides later compare their records through ordinary communication does the special pattern become clear. So Bell's theorem points to something subtler. It says that nature does not fit comfortably inside the combined assumptions of locality, realism, and the usual hidden variable picture. At least one part of that familiar package has to be revised. Different interpretations of quantum mechanics choose different places to make the revision. Some keep the mathematical predictions and give up certain classical ideas of definite pre-existing properties. Some allow non-local hidden variables, as in pilot wave theory associated with Louis de Broglie and David Bohm. Some, like the many worlds interpretation associated with Hugh Everett III, understand measurement in a radically different way. Bell did not force everyone into one interpretation, but he made it much harder to pretend the old assumptions could all remain untouched. The role of measurement settings is what makes the test so powerful. If scientists measured only one property in one fixed way, the results could always look like ordinary correlation. A pair of gloves can pass that test easily. But Bell tests ask several different questions of the particles. They compare the statistics across different measurement choices. The hidden instruction picture then faces a much harder task, because the particles would need to carry answers for all those possible questions while still respecting locality. Quantum mechanics predicts that entangled particles can pass beyond that classical limit. Experiments later showed that they do. This did not close every philosophical doorway, but it did change the landscape forever. Entanglement was no longer only a strange implication of equations or a topic for thoughtful disagreement between Einstein and Bohr. It became an experimental probe of reality itself. Bell gave physics one of its most powerful reality checks. He showed that the strangest connection in the universe was not just strange in language, or strange in mood, or strange because physicists enjoy making perfectly good evenings complicated. It was strange in a measurable way. The universe could be tested, and when tested, it behaved less like a collection of separate objects carrying private instructions, and more like a world where relationships are built deeply into the quantum state. The debate about entanglement began in equations, arguments, and thought experiments, but eventually it had to meet the laboratory. This is one of the quiet strengths of physics. A beautiful idea is not allowed to remain beautiful forever without being asked a few awkward questions by equipment. Sooner or later, it must face mirrors, detectors, cables, timing systems, and the patient suspicion of people who would like nature to be very specific about what it is doing. For entanglement, one of the most useful laboratory tools has been light. More precisely, physicists often work with photons, the particle-like packets of light. Photons are especially useful because they can travel long distances, they can be manipulated with optical equipment, and one of their properties, polarization, can be measured in different carefully chosen ways. Polarization describes the orientation of light's electric field as the light travels. Light is an electromagnetic wave, and its electric field can oscillate in different directions. Some sunglasses use polarizing filters to reduce glare by blocking light polarized in certain directions. In the laboratory, the same broad idea becomes much more precise. A photon can be sent toward a polarization analyzer, and the analyzer is set at a chosen angle. The photon is then detected in a way that gives one of the possible outcomes for that measurement. When entangled photon pairs are used, the two photons are created together in a shared quantum state and sent in different directions. Each photon travels to its own measuring station. At each station, scientists choose a measurement setting, such as a particular polarization angle. Then, detectors record the outcomes. One single pair of photons does not prove very much on its own. Quantum mechanics is not usually generous enough to reveal its deeper structure in one neat click, which is fair enough, though mildly inconvenient. The important evidence comes from repeating the experiment many times and comparing the statistics. Those statistics can then be tested against Bell inequalities. If the photons were simply carrying ordinary hidden instructions, and if no influence travelled between the measuring stations faster than light, the correlations should stay within certain limits. Quantum mechanics predicts that entangled photons can violate those limits. The laboratory question becomes beautifully direct. When real photons are measured, which pattern does nature choose? In the early 1980s, Alain Aspect and his colleagues in France carried out landmark experiments that tested Bell's theorem using entangled photons. These experiments were not the first attempts to explore Bell-type correlations, but they became especially important because of their design and influence. Aspect's work helped move entanglement from a foundational puzzle into a clear experimental program. The question was no longer only whether quantum mechanics seemed philosophically odd. The question was whether the world actually produced the correlations quantum mechanics predicted. Aspect's experiments used pairs of photons emitted by calcium atoms. The photons travelled in opposite directions to separate analyzers where their polarizations were measured. By changing the measurement settings and comparing many results, the experiments tested whether the observed correlations obeyed the limits expected from local hidden variable theories. The results supported quantum mechanics. The photons behaved as entangled particles were predicted to behave. That is a simple sentence, but its meaning is not small. It meant that the strange connection was not just a metaphor borrowed from mathematics. It could be inferred from real patterns in real measurements. A detector clicked here, another detector clicked there. Across many repeated trials, the clicks formed a statistical pattern, and that pattern did not fit the comfortable picture of two particles merely carrying separate pre-written instructions. Later experiments became even more careful. John Clauser had already performed important early Bell test experiments in the 1970s, helping establish that these questions could be tested with real optical systems. Anton Zeilinger and his research groups later developed many influential experiments involving entangled photons, long-distance quantum communication, quantum teleportation, and increasingly refined tests of quantum foundations. Alain Aspect, John Clauser, and Anton Zeilinger were awarded the Nobel Prize in Physics in 2022 for experiments with entangled photons, establishing the violation of Bell inequalities, and pioneering quantum information science. That Nobel Prize was not given because entanglement sounds mysterious in a dramatic documentary voice. It was given because the experimental work showed, again and again, that entanglement is a measurable feature of nature. The experiments also became more sophisticated because real laboratories are never perfect. Detectors can miss photons. Equipment can introduce bias. Measurement stations can be close enough that ordinary signals might, in principle, pass between them during the experiment. The choice of measurement setting might be influenced by some hidden factor in the past. These practical concerns are called loopholes. They do not necessarily mean an experiment is wrong, but they are gaps that careful physicists want to close. Detection efficiency is one issue. If too many photons are missed, perhaps the detected sample is not fully representative of all the pairs created. Communication between measurement stations is another issue. If the stations are not arranged carefully, a skeptic might wonder whether some ordinary physical influence could help coordinate the results. Freedom of measurement choice is also important, because Bell tests depend on the idea that the measurement settings are not secretly prearranged in a way that conspires with the particle's hidden instructions. Over time, experiments were designed to make these loopholes smaller and smaller. Researchers used faster switching of measurement settings, better detectors, longer distances, more precise timing, and improved photon sources. The work involved quantum optics laboratories around the world, including major research settings such as the University of Vienna, the National Institute of Standards and Technology, and the Joint Institute for Laboratory Astrophysics. Each improvement made the evidence more robust. There is something quietly beautiful about this. The question sounds almost cosmic. Can distant particles share a connection that escapes ordinary explanation? But the answer is built from practical acts, aligning beams of light, cooling equipment, calibrating detectors, reducing noise, timing events, and counting results. The universe is asked a delicate question with machinery that must be made almost absurdly careful. Physics often looks grand from a distance, but up close it can resemble someone spending 3 hours persuading one mirror to behave. The result of all this work is not that entanglement has become less strange. In some ways it has become stranger, because the strangeness has survived contact with experiment. The connection between entangled photons is not assumed because someone liked the image. It is inferred because measured correlations repeatedly match the predictions of quantum mechanics and exceed the limits of ordinary local hidden variable pictures. Pairs of light, separated and measured, have helped reveal something profound. The world does not always behave like a collection of independent objects carrying private answers. Sometimes the evidence points to a shared quantum state whose consequences only become visible through careful comparison. The light does not shout the mystery. It arrives in quiet clicks, one photon at a time, until the pattern becomes impossible to ignore. Early Bell tests were powerful, but they were not the end of the story. They showed that real particles could behave in ways that strongly supported quantum mechanics and challenged local hidden variable explanations. But careful physicists are not usually satisfied with, "that looks convincing enough." They are professionally trained to worry about tiny gaps, awkward assumptions, imperfect detectors, suspicious timing, and anything that might let a classical explanation sneak back in through a side door wearing a false moustache. Those possible gaps became known as loopholes. A loophole does not mean an experiment has failed. It means there is a practical feature of the setup that a determined skeptic could point to and say, perhaps there is still another explanation. In ordinary life, this might feel annoyingly fussy. In fundamental physics, it is exactly the right attitude. Entanglement is a profound claim about nature, so the experiments testing it have to be extremely patient, extremely clean, and sometimes almost heroic in their attention to details that most people would not notice unless a laser was pointed at them. One important concern is the locality loophole. The locality loophole is the possibility that the two measurement stations in a Bell test might somehow exchange ordinary signals during the experiment. If the devices are close enough, or if the measurements are slow enough, then perhaps one side could influence the other through some normal physical process travelling at or below the speed of light. That would not explain all the quantum results by itself, but it would weaken the claim that the experiment has truly ruled out local hidden variable explanations. To close this loophole, physicists need separation and timing. The two particles must be sent to measurement stations far enough apart, and the measurement choices and detections must happen quickly enough that no signal limited by the speed of light could pass between the stations in time to coordinate the results. In this way, the experiment tries to make ordinary communication physically unavailable during the crucial moments. Another major concern is the detection loophole. The detection loophole arises because real detectors are imperfect. They do not always register every particle. If too many particles are missed, then the detected particles might not represent the full set of particles created. A local hidden variable theory might, in principle, exploit that missing data by suggesting that the observed sample is biased. Perhaps the particles that were detected happen to be the ones producing the quantum-looking pattern, while the missing particles would have told a more ordinary story. This is why high-efficiency detectors matter so much. A strong Bell test needs to capture enough of the relevant events that the results cannot be dismissed as a selective glimpse of a larger unseen pattern. It is a little like trying to judge an entire orchestra after hearing only the triangle player. The triangle may be doing excellent work, but some context would be useful. For decades, experiments improved steadily, closing different loopholes in different ways. But closing the major loopholes together was technically difficult. The experiment had to create entanglement reliably, separate the systems properly, choose measurement settings quickly and unpredictably, detect outcomes efficiently, and record the timing carefully enough to rule out ordinary coordination. In 2015, several landmark experiments achieved what are often called loophole-free Bell tests. A team led by Ronald Hansen at Delft University of Technology used entangled electron spins associated with nitrogen vacancy centers in diamond. These systems allowed researchers to separate the measurement stations and use high-quality detection of the spin states. Around the same time, researchers connected with the National Institute of Standards and Technology, and other collaborators performed strong photon-based Bell tests using improved detectors. Teams connected to the University of Vienna also contributed to this wave of refined experiments. These tests did not make entanglement suddenly real in 2015. The evidence had been building for decades. But they made the case much stronger by addressing the two most famous practical concerns at once. They showed violations of Bell inequalities under conditions where ordinary communication between the measurement events was ruled out, and where detection was efficient enough to avoid the old sampling worry. Fast random measurement choices were central to this progress. In a Bell test, it matters that each measuring station can choose between different settings. If those choices were somehow prearranged or predictable, a hidden variable model might try to build that information into the particles from the beginning. Modern experiments therefore use fast random number generators to choose measurement settings at the last relevant moment. The goal is to stop the particles, the source, and the measuring devices from sharing a simple hidden plan. Even this has inspired deeper tests. Some physicists have asked whether the random choices might themselves have some hidden connection to the particle source in the shared past. This concern is sometimes linked to the freedom of choice loophole. To push that possibility further away, researchers have designed cosmic Bell tests, using light from distant stars or even quasars to help choose measurement settings. The idea is elegant. If the choice of measurement setting is influenced by light that began travelling from a distant astronomical object long before the experiment, then any hidden coordination would have to reach far back into cosmic history. Experiments using starlight and later light associated with very distant quasars have pushed the possible origin of such coordination billions of years into the past. This does not remove every imaginable philosophical escape hatch, because physics is generous enough to leave a few very odd doors in the building, but it makes ordinary hidden coordination increasingly difficult to take seriously. Closing loopholes strengthens the evidence for quantum entanglement. It shows that the strange correlations are not merely the result of sloppy timing, missed particles, poor detectors, or careless assumptions. They survive when the experiments become stricter. They survive when the measuring stations are separated. They survive when the settings are chosen quickly. They survive when detection improves. Still, this does not mean every deep question has been settled. Bell tests tell physicists something precise and powerful. Nature violates the limits expected from broad classes of local hidden variable theories. They do not force one single interpretation of quantum mechanics onto everyone. Different interpretations still offer different stories about what the mathematics means. But the old comfortable picture of particles simply carrying local prewritten instructions has been pushed very hard. The result is a quieter kind of certainty. Not certainty about every philosophical layer of reality, but certainty that entanglement is not a loose metaphor. It is a measured pattern in nature, strengthened by decades of increasingly careful experiments. The loopholes have not made the mystery disappear. They have made it harder to dismiss. One of the easiest mistakes to make with quantum entanglement is also one of the most tempting. If two particles are entangled, and measuring one of them seems connected with what can be found about the other, then surely this must mean a message has passed between them. Perhaps one particle somehow tells the other what happened. Perhaps the universe has found a private shortcut through space. Perhaps, hidden beneath reality, there is a tiny quantum messaging service running with suspiciously good coverage. But that is not what entanglement allows. Entanglement does not let anyone send useful messages, commands, warnings, or conversations instantly between distant places. It does not provide faster-than-light communication. It does not allow someone on one side of the galaxy to tap out a signal and have someone on the other side receive it at once. The connection is real, but it's not a controllable communication channel. This matters because the popular version of entanglement often sounds as if it directly breaks Albert Einstein's special theory of relativity. In 1905, Einstein showed that the speed of light is not just the speed of one particular thing moving through space. It is built into the structure of space-time itself. In special relativity, usable signals, causes, and information cannot travel faster than light. This limit is not a minor traffic rule for photons. It is part of how the universe keeps cause and effect from becoming a deeply confusing soup. At first glance, entanglement seems to threaten that rule. Two particles are created in a shared quantum state, then sent far apart. When one is measured, the result is correlated with the result found for the other. If the particles are separated by a huge distance, the connection can seem instant. That is where the imagination starts sprinting enthusiastically in the wrong direction. The key difference is the difference between correlation and communication. A correlation means that two sets of results are related. Communication means that one side can deliberately send a chosen message to the other. Those are not the same thing. A pair of clocks might show the same time because they were synchronized earlier. That is correlation, not communication. A pair of shoes in separate boxes might be related, because finding the left shoe in one box means the right shoe is in the other. Again, that is not a message being sent. It is a pattern revealed when the information is compared. Entanglement is more subtle than clocks or shoes, but the same distinction is vital. When a person measures one particle in an entangled pair, they do not get to choose the result. The outcome, from their local point of view, appears random. They might measure a photon's polarization and get one possible result, or another possible result, according to the probabilities given by quantum mechanics. But they cannot decide. I would like this result now because it shall mean hello, and then produce that outcome on command. That lack of control prevents faster-than-light messaging. Suppose two observers share many entangled particle pairs. One observer is far away from the other. Each measures their particles. Locally, each observer sees a string of results that looks random. The first observer cannot arrange their results into a chosen sentence. The second observer cannot look at their own results alone and read a message. Nothing in the local list says, "Good evening from the other laboratory," or "Please bring biscuits," although many scientists would probably appreciate the latter. Only later, when the two observers compare their records through ordinary communication, does the special pattern appear. They have to bring the list together, or send the data by light signal, radio wave, fiber optic cable, or some other ordinary method. That comparison is still limited by the speed of light. Until the records are compared, the correlations cannot be used as a message. This principle is called the no communication theorem. In plain language, it says that quantum entanglement cannot be used to transmit usable information faster than light. The entangled measurements may be correlated in a way that violates Bell inequalities, but each local outcome remains uncontrollable and random. The pattern is real, but it only becomes visible after ordinary communication has done its slower, less glamorous work. This is one of the reasons entanglement is so interesting. It seems to reach across distance without becoming a signal. It challenges simple ideas of separateness, while still respecting the cosmic speed limit for usable information. It is as if nature allows a deep relationship between the parts of a quantum system, but refuses to let that relationship become a faster-than-light telephone. That may sound like a technical limitation, but it preserves something important. If entanglement allowed controllable instant messages, special relativity would be in serious trouble. Cause and effect could become tangled across different frames of reference. In some situations, one observer might disagree with another about the order of events, and faster-than-light signals could open the door to logical paradoxes. Physics is strange enough already without allowing someone to receive a reply before sending the question. So entanglement sits in a delicate place. It is not ordinary, and it is not classical. It reveals correlations that cannot be explained by simple, local hidden instruction models. Yet it does not let information race across space in a usable way. It unsettles the old picture of independent particles, but it does not simply overthrow relativity. The mystery, then, is not that entanglement lets particles chat faster than light. The mystery is deeper and quieter. Two separated particles can belong to one shared quantum state, and their measurement results can show a relationship stronger than ordinary classical thinking allows. But no one can control the individual outcome. No one can turn the correlation into a private signal, and no one can use it to send a message instantly through the dark. Entanglement does not make the universe a place of magical shortcuts. It makes it a place where connection and communication are not the same thing. And once that distinction is clear, the strangeness does not disappear. It becomes cleaner, sharper, and more remarkable. Measurement is where quantum mechanics becomes quiet, precise, and deeply uncomfortable. Before measurement, quantum theory can describe a system through a range of possible outcomes. It does not always say that one ordinary result is already sitting there, fully formed, waiting to be uncovered like a coin under a cup. Instead, the quantum state gives probabilities. It tells physicists what outcomes can appear and how likely those outcomes are when a particular measurement is performed. Then the measurement happens. A detector clicks. A mark appears on a screen. An atom is found in one energy state rather than another. A photon passes through one polarizing filter and not another. Out of the spread of possible results described by the quantum state, one actual result is recorded. The soft cloud of possibility becomes a hard little fact in the laboratory notebook, which is a very dramatic event for something that may look like a tiny flash on a sensor. This is the center of the measurement problem. The measurement problem asks how definite outcomes arise from quantum possibilities. Quantum mechanics gives an extraordinarily successful rule for predicting probabilities. It tells scientists how often different results should appear if the same experiment is repeated many times under the same conditions. But it is much less straightforward when asked what exactly happens during a single measurement. Does the quantum state physically collapse? Does the measuring device become entangled with the system? Does the universe split into different branches? Is there some deeper process missing from the standard theory? These questions are not fringe decorations around quantum mechanics. They sit very close to its foundations. The Copenhagen interpretation, associated especially with Niels Bohr and Werner Heisenberg, treats measurement as a central part of what quantum theory is about. In this broad view, quantum mechanics does not simply reveal hidden classical properties that were already there in the familiar way. It gives rules for what can be predicted and observed under defined experimental arrangements. The measuring setup matters because it helps determine which question nature is being asked. This view has been enormously influential, but it can feel unsatisfying to anyone who wants a clear picture of what is happening behind the measurement. It often tells physicists how to calculate results very well, while leaving the deeper story somewhat restrained. Bohr might have said that this restraint is wisdom. Many students quietly suspect it is also a very elegant way of making the universe hard to argue with. The many worlds interpretation associated with Hugh Everett, the third, takes a different path. It suggests that the quantum state never collapses in the usual sense. Instead, all possible outcomes described by the quantum state occur in different branches of reality. When a measurement is made, the observer and measuring device become part of this branching structure. From inside one branch, only one outcome is experienced, even though the full quantum state contains all of them. Pilot wave theory, associated first with Louis de Broglie and later developed by David Bohm, offers another route. In this view, particles do have definite positions, guided by a real wave-like structure. The theory is deterministic, meaning the outcomes are fixed by the underlying state, but it is also non-local in a deep way. It preserves definite particle properties, but it does so by allowing the guiding structure to connect distant parts of a system in a manner that does not fit ordinary classical locality. Objective collapse ideas take yet another approach. Theories associated with Giancarlo Ghirardi, Alberto Rimini and Tullio Weber propose that the quantum state really does collapse, but not merely because someone looks. Instead, collapse is treated as a physical process that happens spontaneously under certain conditions. Roger Penrose has also explored the possibility that gravity may play a role in wave function collapse, though this remains speculative and not part of established consensus. These interpretations often agree about the experimental predictions that have been tested so far. That is part of what makes the issue so subtle. They can produce the same numbers, the same detector clicks, and the same successful laboratory results, while telling very different stories about what reality is doing underneath. It is a little like several people giving correct directions to the same village while disagreeing intensely about whether the road itself truly exists, branches into many roads, or is being guided by an invisible map. It is also important to avoid one very common misunderstanding. Quantum measurement does not require human consciousness in the mystical sense. A detector does not need to feel surprised. A photographic plate does not need to become self-aware. A measuring device is a physical system that interacts with the quantum system being measured, producing a stable record that can later be read. In modern discussions, the environment also matters, because surrounding air molecules, light, heat, and equipment can become involved in the process. So when quantum physics speaks of an observer, it does not have to mean a person staring dramatically at a particle. It can mean a physical interaction that records information about the system. Conscious human awareness may come later, when someone looks at the data, but the laboratory does not wait for a physicist to sip coffee and approve reality before a detector registers an event. Entanglement makes measurement feel even more consequential. When two particles are entangled, they are described by one combined quantum state. Measuring one part of the system changes how physicists describe the whole. It does not allow a controllable faster-than-light message, and it does not mean one observer can choose the distant result. But it does mean that after one measurement has been made, the predictions for the other part of the system are updated in a precise way. This is why entanglement sharpens the measurement problem. With a single particle, measurement already raises the question of how possibility becomes outcome. With two entangled particles, that question stretches across distance. A measurement in one place is tied to the structure of predictions about another place, even when no ordinary signal can be used to send information faster than light. The issue is not that physics has become vague. The predictions are clear. The experiments are precise. The correlations can be measured. The difficulty is that the meaning behind the mathematics remains open to interpretation. Quantum mechanics tells scientists what to expect with astonishing reliability, but it does not hand over one universally accepted picture of what measurement truly is. At the center of entanglement, then, sits a quiet problem. A quantum state describes possibilities. A measurement records one result. An entangled system links those results in patterns that ordinary hidden instruction models cannot reproduce. Somewhere in that transition from possibility to fact, the universe reveals both its precision and its refusal to behave like a tiny version of everyday common sense. The quantum world often sounds as if it should be visible everywhere. If atoms and particles obey quantum rules, and if everything around us is made of atoms and particles, then a fair question appears. Why does the everyday world not behave like an entanglement experiment? Why does a table not sit in a delicate superposition of several positions? Why does a teacup not behave like a carefully prepared photon? Why does a chair remain a chair, instead of becoming a philosophical crisis with legs? Part of the answer is decoherence. Decoherence is the process by which delicate quantum relationships become effectively hidden when a quantum system interacts with its environment. It does not mean the quantum rules stop applying. It means that the fragile, observable features of quantum behavior become spread into the surrounding world so quickly and so thoroughly that they can no longer be seen as a clean superposition or a useful entangled state. A quantum system is easiest to study when it is isolated. A photon travelling through a carefully aligned optical setup, an ion held in an electromagnetic trap, or an atom cooled close to absolute zero can preserve delicate quantum behavior long enough for physicists to measure it. But the moment a quantum system interacts with its surroundings, the situation becomes much messier. Air molecules bump into it. Stray photons scatter from it. Heat jostles it. Vibrations nudge the apparatus. Surfaces absorb and emit tiny amounts of energy. The environment does not politely stand aside while the quantum system has its mysterious little moment. Instead, the environment becomes involved. This is important because entanglement does not only happen between neat pairs of laboratory particles. In principle, a quantum system can become entangled with many surrounding systems. A particle prepared in a delicate state may interact with a molecule in the air. That molecule may interact with another molecule. A photon may carry away information. A surface may record some trace of the interaction. Very quickly, the original clean quantum relationship is no longer contained in the simple system physicists hope to observe. It has leaked into a wider, more complicated web. Wojciech Zurek has been one of the major figures in the modern study of decoherence. His work helped explain why the everyday world appears classical, even though it is built from quantum components. The idea is not that large objects are secretly exempt from quantum mechanics. It is that large objects are constantly interacting with their environments in so many ways that certain quantum possibilities become effectively inaccessible. The weirdness has not vanished in a magical puff of dust. It has been dispersed into correlations with the world around it, which is somehow less theatrical and more devastating. This helps explain why quantum superpositions are so hard to observe in large, warm, messy systems. A tiny, isolated system can sometimes preserve a superposition long enough to be studied, but a warm object made of enormous numbers of particles is continually exchanging energy and information with its surroundings. It radiates heat, it reflects light, it vibrates, it collides with air molecules. Each of these interactions can carry away information about the object's state, and that information spreading into the environment destroys the clean interference effects that would otherwise reveal the superposition. This is why a dust grain floating in sunlight does not behave like a pristine quantum experiment. It is being struck by photons, warmed by radiation, tugged by air currents, and surrounded by molecules. A teacup on a table is even worse, at least from the point of view of delicate quantum purity. It is warm, it is solid, it contains trillions upon trillions of particles, all interacting with each other and with the room. If it ever had ambitions of behaving like an isolated electron, the surrounding universe politely but firmly ruined them almost instantly. Decoherence also helps explain why the everyday world has such a stable, classical appearance. Tables, chairs, planets, cups, and people seem to have definite positions and ordinary properties because their quantum alternatives do not remain cleanly observable. The environment effectively selects stable states that can persist and be recorded. This idea is often connected with Zurek's work on einselection, meaning environment-induced superselection. In gentle terms, the environment favours certain robust states and rapidly hides delicate combinations of alternatives. Still, decoherence does not solve every interpretation of quantum measurement. It explains why quantum superpositions become practically invisible in large systems. It explains why interference disappears when a system becomes entangled with its surroundings. It explains why the world looks classical, even though quantum mechanics underlies it. But it does not fully answer the deeper question of why one definite outcome is experienced in a measurement. Different interpretations of quantum mechanics use decoherence in different ways. The Copenhagen interpretation, many worlds interpretation, pilot wave theory, and objective collapse theories may all treat its meaning differently. So decoherence is not the final sentence in the story. It is more like the missing bridge between microscopic strangeness and everyday calm. It shows why quantum weirdness is not usually absent, but hidden by interaction. The world does not need to be watched by a conscious mind to become ordinary. It is already being watched, in a physical sense, by light, air, heat, dust, walls, instruments, and everything else touching everything else. This matters deeply for entanglement. To preserve entanglement, physicists must protect quantum systems from unwanted environmental contact. They use vacuum chambers to remove air molecules. They cool systems to extremely low temperatures to reduce thermal noise. They isolate equipment from vibration. They shield experiments from stray electromagnetic fields. In some quantum computers, superconducting circuits operate at temperatures far colder than interstellar space, not for dramatic effect, but because warmth is relentless gossip that tells the environment too much. Preserving entanglement is therefore not only a philosophical challenge, it is an engineering challenge. It requires controlling matter, light, temperature, noise, timing, and measurement with extraordinary care. The same fragility that makes entanglement feel mysterious also makes it difficult to use, and that is why the strange connection usually stays hidden from ordinary life. The universe around us is not quiet enough, cold enough, or isolated enough for delicate quantum relationships to remain visible for long. The weirdness disappears not because it was unreal, but because everything is connected to everything else a little too enthusiastically. For much of its early life, entanglement was treated as a puzzle about reality. It was the strange feature that troubled Einstein, sharpened the EPR argument, and gave Bell's theorem its power. It forced physicists to ask whether distant systems could really have independent properties, whether hidden variables could explain quantum probabilities, and whether the world was less separable than it appeared. For a long time, entanglement seemed like a question whispered from the foundations of physics, the kind of question that makes the room go quiet and the chalkboard look slightly suspicious. But over time, something changed. Physicists did not stop treating entanglement as profound. They simply began treating it as useful as well. The strangest connection in the universe became not only a mystery to be interpreted, but a resource to be created, measured, protected, moved around, and used. This shift helped give rise to quantum information science. Information in ordinary life is something that can be stored, copied, transmitted, processed, lost, protected, or corrupted. A book contains information. A computer file contains information. A message sent through a fiber optic cable carries information. In classical information theory, the basic unit is the bit, which can take one of two values. It can be one option or the other, like yes or no, on or off, heads or tails. The bit is simple, but from enough simple bits, entire digital worlds can be built. Quantum information uses a different basic unit, the qubit, or quantum bit. A qubit can be represented by many physical systems. It might be the internal energy levels of an atom. It might be the polarization of a photon. It might be the spin state of an electron. It might be the state of a trapped ion held in place by electromagnetic fields. It might be a tiny superconducting circuit cooled to extremely low temperatures. The physical forms differ, but the shared idea is that a qubit follows quantum rules. A qubit is not simply a classical bit wearing a more expensive hat. It can exist in a superposition of possible measurement outcomes, and qubits can become entangled with one another. This makes quantum information different from ordinary information in a fundamental way. It cannot always be copied freely. It can be disturbed by measurement. It can be spread across a combined quantum state, so that the information is not located neatly in one part alone. This is where entanglement becomes a resource. In modern quantum information science, entanglement can be created between physical systems distributed across distance, measured through statistical tests, protected from environmental noise, and consumed in tasks such as quantum teleportation or certain forms of quantum communication. The word consumed may sound odd, as if entanglement were a snack kept in a laboratory cupboard. But in technical terms, it means that entanglement can be used up as part of a protocol. A shared entangled state may enable a task, and once the task is complete, that particular entangled resource is no longer available in the same form. This practical view of entanglement grew through the work of many scientists. Charles Bennett and Gilles Brassard helped establish major ideas in quantum cryptography and quantum information. William Wouters contributed deeply to the theory of quantum information and entanglement. Asher Perez worked on the foundations of quantum mechanics and helped clarify how entanglement could be understood and tested. Together with others, these researchers helped move entanglement from the edge of philosophical debate into the center of a developing scientific field. One of the great insights was that entanglement could be counted, compared, and classified in different ways. That does not mean there is one simple universal entanglement meter that can be pointed at any system while making a cheerful little beep. Different systems require different measures. 2 qubits may be analyzed differently from a large many-particle material. Pure quantum states may be treated differently from mixed states, affected by noise and uncertainty. One important concept is entanglement entropy. In gentle terms, entanglement entropy is a way of describing how much quantum information is shared between parts of a system. If 2 parts are not entangled, each can be described more independently. If they are strongly entangled, the description of one part is deeply tied to the description of the other. Entanglement entropy gives physicists a mathematical way to express that relationship, especially in larger quantum systems, quantum field theory, and studies of black holes. This is a remarkable transformation. The same feature that once seemed like an embarrassment to common sense became something physicists could use as a tool. Entanglement was no longer only the thing that made Einstein uneasy. It became the thing that allowed new protocols to exist. Quantum teleportation is one example. It does not teleport objects or people, and it does not work like science fiction transporters. Instead, it uses shared entanglement and ordinary classical communication to transfer an unknown quantum state from one system to another. Quantum key distribution is another example, where quantum principles can help reveal whether an eavesdropper has disturbed a communication channel. Quantum computing is another, where entanglement can be one ingredient in processing information in ways not available to ordinary classical machines. Major research communities now study these ideas across the world. IBM Quantum, Google Quantum AI, Microsoft Quantum, the National Institute of Standards and Technology, and many university quantum laboratories work on different parts of the problem. Some focus on superconducting circuits. Some work with trapped ions. Some use photons. Some study neutral atoms, quantum dots, defects in diamond, or other physical platforms. The field is broad, technically difficult, and still developing. It is important not to turn this into an advertisement for a finished technological revolution. Quantum information science is powerful, but many practical systems remain fragile, noisy, expensive, and hard to scale. Preserving entanglement is difficult. Correcting quantum errors is difficult. Building useful large-scale quantum devices is difficult. The universe has provided the rules, but it has not kindly included a simple instruction manual, which feels a little inconsiderate. Still, the direction is clear. Entanglement is not merely a poetic mystery. It is measurable, it has structure, it can be generated in the laboratory, it can be degraded by the environment, it can be tested through Bell inequalities, it can be used in carefully designed protocols, it can be studied as a kind of physical information, and this brings the title into sharper focus. Quantum entanglement may be the strangest connection in the universe, but it is not strange in a vague or decorative way. Its strangeness has rules. It can be handled with mathematics, equipment, patience, and very cold machinery. What once looked like an awkward philosophical disturbance has become one of the most important resources in modern physics. The connection is still mysterious, but it is no longer only something to wonder at from a distance. It is something science has learned to hold, measure, protect, and use. Quantum teleportation is real, which is both exciting and slightly misleading. The name sounds as if it belongs to a glowing platform on a starship, where someone steps into a beam of light and appears somewhere else, with their hair only mildly rearranged. But quantum teleportation does not move a person through space. It does not move an object through space. It does not even move a particle through space in the ordinary sense. No atom is dissolved here and rebuilt over there. No laboratory technician is accidentally transported into a coffee machine, which is probably best for everyone involved. Quantum teleportation is stranger, quieter, and much more precise. It is a real quantum information protocol for transferring an unknown quantum state from one physical system to another. The state is transferred, not the material object itself. The original system is measured in a way that destroys the original version of that quantum information, while another system elsewhere is adjusted so that it carries the state. The idea was proposed in 1993 by Charles Bennett, Gilles Brassard, Claude Crépeau, Richard Joza, Asher Perez, and William Wouters. Their work showed that entanglement could be used as a resource in a task that had no classical equivalent. The proposal was not a piece of science fiction. It was a careful result in quantum information theory, and it revealed something profound about what entanglement can do. To see the idea gently, imagine that one laboratory has a quantum system in an unknown state. This might be the polarization state of a photon, the internal state of an atom, or the state of a trapped ion. The challenge is to transfer that unknown quantum state to another system in a distant laboratory. In ordinary life, copying information sounds easy. If there is a message on a page, it can be photographed, scanned, typed, copied, pasted, and sent to someone who will probably still reply thanks 3 days later. Quantum information is not like that. One reason is the no-cloning theorem. In quantum mechanics, an unknown quantum state cannot be perfectly copied while leaving the original intact. This is not a problem of poor equipment. It is a rule built into the structure of quantum theory. So quantum teleportation does not make a spare copy. Instead, it transfers the state from one system to another, while the original is no longer available in its original form. The protocol begins with entanglement. Two systems are prepared in an entangled state. One is kept near the sender, and the other is sent to the receiver. These two systems now share a quantum relationship. They are separate in space, but their combined state carries a structure that can be used. Then the sender takes the unknown quantum system and the nearby half of the entangled pair and performs a joint measurement on them. This measurement is not just a casual glance. It is a special kind of quantum measurement that links the unknown state with the sender's entangled system. Once this measurement is made, the original unknown state is no longer sitting there as it was. It has been consumed by the process, which sounds dramatic, but in physics mostly means that the information has been transformed through measurement. The sender's measurement produces an ordinary result. That result is not the full quantum state. It is classical information, the kind that can be written down, sent in a normal message, or transmitted through a regular communication channel. The sender must then send this ordinary information to the receiver. This step is essential. Because ordinary classical communication is required, quantum teleportation cannot be used to send information faster than light. The receiver cannot complete the process until the sender's message arrives. If the laboratories are separated by a great distance, that message is still limited by the speed of light, just as Albert Einstein's special relativity requires. Entanglement provides the strange shared resource, but classical communication provides the necessary instruction. The universe allows the trick, but only after checking the rules at the door. Once the receiver gets the classical information, they apply a corresponding adjustment to their half of the entangled pair. After that adjustment, the receiver's system carries the original unknown quantum state. The state has been transferred from the sender's system to the receiver's system without the original physical particle travelling across the distance. That is quantum teleportation. It is a beautiful example of how entanglement behaves like a strange connection without becoming a faster-than-light message. The entangled pair is necessary. The joint measurement is necessary. The ordinary communication is necessary. No single part of the process can do the whole job alone. Remove the entanglement and the protocol fails. Remove the classical message and the receiver cannot reconstruct the state. Try to use it to send instant information, and the universe politely refuses, possibly while wearing the expression of a very patient examiner. Quantum teleportation has been demonstrated in real experiments. Early demonstrations used photons, because photon polarization can carry quantum information, and photons can travel through optical systems. Anton Zeilinger and his collaborators were among the major figures associated with experimental quantum teleportation and long-distance entanglement work. Later experiments extended teleportation to other systems, including trapped ions and atoms, where quantum states can be controlled with remarkable precision. Researchers have also explored increasingly long-distance optical links. Jianwei Pan and his research groups in China have played a major role in long-distance quantum communication, including satellite-based experiments using entanglement and quantum teleportation concepts. These demonstrations show that quantum teleportation is not merely a theoretical curiosity. It is part of a growing experimental field, connected to quantum networks, quantum repeaters, and future attempts to transmit quantum information between distant devices. Still, it is important to keep the scale of the achievement clear. Quantum teleportation does not mean matter transportation. It is not a shortcut for moving spacecraft, sandwiches, or sleepy scientists across the room. It is the transfer of quantum state information from one system to another, using entanglement and ordinary communication together. That may sound less theatrical than fiction, but scientifically it is much more interesting. It reveals that the identity of a quantum system, in a certain carefully defined sense, can be separated from the physical object that first carried it. The state can be relocated, not by copying, not by pushing the particle through space, and not by sending a faster-than-light signal, but by using an entangled relationship and a classical message. This is why quantum teleportation belongs so naturally in the story of entanglement. It shows the strange connection doing real work. The shared quantum state is not merely something to wonder about from a distance. It becomes part of a protocol, a tool, a method for moving quantum information while still obeying the limits of relativity. Entanglement remains mysterious, but here the mystery has a job. It carries no voice across the stars. It breaks no cosmic speed limit. It simply allows the universe to perform a task that ordinary intuition would never have guessed was possible. Quantum computers are often described as if they are powered by entanglement alone, as though entanglement is a kind of glowing fuel poured into a very expensive machine until it begins solving problems in a mysterious blue haze. The real story is more careful than that. Entanglement is deeply important in quantum computing, but it is not the whole explanation by itself. Quantum computers rely on several connected ingredients: qubits, superposition, interference, quantum gates, measurement, and, in many useful situations, entanglement. Each part matters. Remove one piece, and the whole machine becomes less like a revolution in computation, and more like a very cold cupboard full of wires. A classical computer uses bits. Each bit is in one of two possible states, often described as 0 or 1. Enough bits, arranged and processed in clever ways, can store text, images, music, video, calculations, and the deeply important information that someone has once again forgotten their password. A quantum computer uses qubits, or quantum bits. A qubit can be made from many different physical systems. It might be the state of a trapped ion. It might be a superconducting circuit cooled to extremely low temperatures. It might be the polarization of a photon, the spin state of an electron, or the energy levels of an atom. The physical form can vary, but the qubit must obey quantum rules. A qubit can be prepared in a superposition of possible measurement outcomes. This does not mean it is magically both ordinary values in a vague way. It means the quantum state contains probability amplitudes, which determine how likely different outcomes are when the qubit is eventually measured. When many qubits are used together, their possible states can interfere with one another. Interference is crucial because quantum algorithms are not simply about trying every answer at once. They're about arranging quantum evolution so that wrong paths tend to cancel out and useful answers become more likely. Quantum gates are the operations used to change qubit states. They are the quantum version of logical operations in ordinary computing, but they act according to quantum mechanics. Some gates rotate the state of a single qubit. Others connect 2 or more qubits. These multi-qubit gates can create entanglement, making the state of the whole system impossible to describe as separate independent states for each qubit. This is where entanglement enters the machinery. In many quantum circuits, entanglement allows information to be spread across the system in a way that has no direct classical equivalent. The qubits no longer behave like isolated switches. Their joint state carries patterns of relationship, and those patterns can be shaped by quantum gates and interference. A useful quantum computation is not just a crowd of qubits being individually strange. It is a carefully choreographed evolution of a shared quantum state. The dream of quantum computing was shaped by several major figures. Richard Feynman argued in the early 1980s that ordinary computers struggle to simulate quantum systems because nature itself is quantum. A classical machine must work very hard to track all the possibilities in a quantum system, especially as the number of particles grows. Feynman suggested that a computer built from quantum principles might simulate quantum physics more naturally. David Deutsch later helped formalize the idea of a universal quantum computer. This was a major conceptual step, showing that quantum computation could be studied as a general model rather than just a special tool for one problem. From there, the field grew into one of the most ambitious areas of modern physics and computer science. One of the most famous breakthroughs came from Peter Shor in the 1990s. Shor developed a quantum algorithm for factoring large numbers efficiently, at least on a sufficiently powerful fault-tolerant quantum computer. This matters because some widely used cryptographic systems depend on the difficulty of factoring large numbers with classical computers. Shor's algorithm showed that quantum computers were not just interesting for simulating atoms. They could, in principle, change what kinds of problems are considered practically difficult. Love Grover developed another important quantum algorithm, usually known as Grover's search algorithm. It offers a speed-up for searching through an unstructured collection of possibilities. It is not the magical ability to instantly find anything, anywhere, which would be useful mostly for keys, socks, and that one missing file called final version final. But it is a genuine quantum advantage for a broad kind of task. Still, quantum computers are difficult to build for the same reason the entanglement is difficult to preserve. Qubits are fragile. They interact with their environment: heat, vibration, stray electromagnetic fields, imperfect control pulses, Material defects and measurement errors can disturb the quantum state. Decoherence can destroy the delicate superpositions and entanglement needed for computation. Noise does not have to be dramatic. It only has to be persistent, and the universe is very good at persistent. This is why many quantum computing platforms require extreme conditions. Superconducting qubits are often cooled to temperatures only slightly above absolute zero. Trapped ion systems use lasers and electromagnetic fields to hold and control individual charged atoms. Photonic systems require precise optical components and low-loss pathways. Neutral atom systems use laser light to trap and arrange atoms. Each approach has strengths, weaknesses, and an impressive number of ways to make engineers sigh quietly. Because quantum information is so delicate, quantum error correction has become essential. Peter Shaw, Andrew Steen, and Daniel Gottsman are among the major figures associated with this field. The basic idea is that a single logical qubit can be protected by spreading its information across many physical qubits. This is subtle, because quantum information cannot simply be copied in the ordinary way. Error correction must detect and repair certain kinds of errors without directly measuring and destroying the quantum information being protected. This means a useful large-scale quantum computer may need many physical qubits to create one reliable logical qubit. It also needs gates that are accurate enough, measurements that are reliable enough, and error rates low enough for correction to keep up. This is the path toward fault-tolerant quantum computing, where computations can proceed despite noise and imperfections. Current quantum computers are real. They can perform quantum operations, create entanglement, run experimental algorithms, and simulate certain systems, but they are still limited. Many devices today are noisy, relatively small, and not yet capable of the large-scale fault-tolerant computation needed for the most transformative applications. So entanglement is not a magic ingredient that makes computers instantly all-powerful. It is one part of a larger quantum structure, working with superposition, interference, gates, measurement, and error correction. The fragile link that once troubled Einstein has become a tool engineers try to protect, stretch, and control. And that is one of the most remarkable turns in the story. The strangest connection in the universe is no longer only a philosophical challenge, it is also a fragile thread inside machines that may one day help explore chemistry, materials, optimization, cryptography, and the quantum behavior of nature itself. Quantum cryptography begins with a beautifully practical question. If information is precious, how can it be protected? A message can be encrypted, hidden, scrambled, and guarded behind mathematics. But any secret message has a quiet problem sitting underneath it. Somewhere, somehow, the people communicating need a key. A cryptographic key is the shared secret that allows the message to be locked and unlocked. If the key is safe, the message can be safe. If the key is stolen, the most elegant code may suddenly become about as private as a postcard left on a cafe table. Quantum cryptography is a field that uses quantum principles to help secure communication. The popular phrase, unbreakable code, is often attached to it, but that phrase is too simple. Real systems are messier, and security always depends on assumptions, hardware, implementation, and careful design. Quantum cryptography is not a magic shield. It's a way of using the behavior of quantum systems, especially measurement and sometimes entanglement, to detect whether a communication channel has been disturbed. One of the central ideas is quantum key distribution. The aim is not usually to send the message itself in a strange quantum form. The aim is to help two parties create a shared secret key. Once they have that key, they can use it with ordinary encryption methods. What makes the quantum part special is that any eavesdropper trying to inspect the quantum signals may leave traces, because measurement in quantum mechanics is not always passive. It can disturb the state being measured. A famous early protocol is called BB84, developed by Charles Bennett and Gilles Brassard in 1984. In this approach, quantum states, often represented by individual photons, are prepared and measured in different possible ways. If someone secretly intercepts and measures those photons, they cannot usually do so without introducing errors that the legitimate users can later detect. The security comes from quantum measurement itself, not from hoping an eavesdropper is too polite to look. Entanglement brought another path. Arthur Eckert proposed an entanglement-based form of quantum key distribution in 1991. In this kind of approach, two distant users share pairs of entangled particles and measure them. Because entangled particles produce special correlations, the users can compare part of their data to check whether the shared quantum link behaved as expected. Bell-type correlations can be used as a test. If the correlations look right, the users gain confidence that the entangled system has not been tampered with in a way that would compromise the key. This is where the abstract mystery of entanglement begins to feel unexpectedly practical. The same strange connection that troubled Einstein, sharpened Bell's theorem, and filled laboratories with careful photon experiments can also become part of a security protocol. It is not just a philosophical puzzle admired from a distance. It can help protect information. Still, real quantum communication is not effortless. Photons can be lost as they travel through optical fibers or across open-air links. Detectors can be imperfect. Equipment can have flaws. A system may be secure in theory but vulnerable in practice if the hardware behaves in unexpected ways. Security does not live only in elegant equations. It also lives in cables, lasers, timing electronics, calibration, shielding, and the unfortunate habit of real devices to be more complicated than diagrams suggest. Distance is another challenge. Optical fibers absorb and scatter photons, so quantum signals weaken as they travel. Classical communication can be amplified along the way, but unknown quantum states cannot simply be copied and boosted because of the no-cloning theorem. This makes long-distance quantum communication difficult. Researchers explore trusted nodes, where intermediate stations help extend the network, though those nodes must themselves be secure. They also explore satellites, because photons travelling through space can sometimes avoid much of the loss found in long fibers. China's Messius satellite, associated with work by Jianwei Pan and his research group, became a major demonstration of long-distance quantum communication. It showed that entangled photons and quantum key distribution ideas could be extended over very large distances using satellite links. These experiments did not create a finished global quantum internet overnight, which is probably for the best, because the universe rarely delivers major infrastructure before breakfast. But they did show that quantum communication can move beyond a single laboratory and operate across real geographical scales. Authentication is also essential. Quantum key distribution can help reveal eavesdropping on the quantum channel, but the users still need a way to know they're talking to the right party in the first place. Otherwise, an attacker might impersonate someone else. This is why real security systems combine quantum methods with classical cryptographic procedures. The quantum part is powerful, but it is not a complete replacement for every other layer of security. Entanglement-based protocols are especially interesting because they use the very feature that once seemed most unsettling. Bell-type tests can help check whether the observed correlations are genuinely quantum and whether the link behaves as expected. In some advanced ideas, security can be tied very closely to the violation of Bell inequalities, making the strange statistical pattern itself part of the evidence that the key has been generated safely. So quantum keys reveal a quieter side of entanglement. The strange connection is not only a doorway into deep questions about reality, it is also a possible tool for protecting messages in a world where information has become one of the most valuable things people send, store, and steal. The field remains technically demanding, full of engineering obstacles and careful caveats, but the central idea is remarkable. By using the fragility of quantum measurement and sometimes the correlations of entanglement, physics can help reveal when secrecy has been disturbed. The universe does not hand over perfect privacy, but it does offer a strange and delicate warning system written into the rules of quantum mechanics themselves. Entanglement is often introduced through light, because photons are wonderfully useful messengers. They can travel long distances, carry polarization states, pass through optical equipment, and arrive at detectors as neat little clicks. Many of the most famous tests of Bell's theorem used entangled photons, and it is easy to let them become the main characters of the whole story. But photons are not the only place where entanglement appears. The strange connection is far more widespread than that. Entanglement can appear in atoms, ions, electrons, superconducting circuits, quantum dots, and large many-particle systems inside materials. It is not a rare decorative trick that only happens when physicists persuade light to behave unusually in a carefully aligned laboratory. It is part of the wider language of quantum mechanics. Wherever quantum systems can share a state that cannot be separated neatly into independent parts, entanglement can enter the picture. This becomes especially important in condensed matter physics. Condensed matter physics is the study of materials and many particle systems. It asks how enormous numbers of atoms, electrons, and other quantum components behave together. A single electron is already a quantum object, but a material contains vast numbers of interacting electrons and atomic nuclei, all arranged in patterns, jostling, exchanging energy, and producing large-scale behavior. Out of that collective activity come familiar properties such as electrical conductivity, magnetism, heat capacity, crystal structure, and elasticity. Out of it also come stranger phenomena such as superconductivity, superfluidity, topological phases, and quantum magnetism. Philip Anderson was one of the major figures in condensed matter physics. He helped show that many particle systems cannot always be understood simply by taking the behavior of one particle and multiplying it by a large number. His famous phrase, "more is different," captures the idea beautifully. When many parts interact, new kinds of order can emerge. A material is not just a crowd of atoms standing politely in formation. It can become a stage for collective quantum behavior. In these many body systems, correlations can be far richer than the simple, pairwise entanglement often used in introductory examples. Two photons in an entangled state are already strange enough. But inside a material, enormous numbers of particles can have relationships woven through the whole system. These relationships can influence the phase of matter the material enters, how it responds to magnetic fields, how it conducts electricity, and how its quantum information is spread across space. Magnetism offers one route into this idea. In some materials, electron spins interact with one another. Spin, again, is not a literal tiny rotation like a planet turning in space, but an intrinsic quantum property. In a ferromagnet, many spins tend to align, producing a magnetic field. In more exotic quantum magnets, spins can become correlated in subtler ways. Some systems may form quantum spin liquids, phases where the spins do not settle into a simple ordered pattern, even at extremely low temperatures. Entanglement can be an important part of describing these unusual states. Superconductivity is another famous example of coherent quantum behavior in matter. A superconductor is a material that can carry electrical current without electrical resistance below a certain critical temperature. In conventional superconductors, electrons form paired states known as Cooper pairs, named after Leon Cooper. These pairs are part of the Bardeen-Cooper and Schrieffer theory of superconductivity, developed by John Bardeen, Leon Cooper, and John Robert Schrieffer. It is important to be careful here. Superconductivity should not be described as simply ordinary pairwise entanglement between electrons, as if every superconductor were just a cupboard full of tiny entangled couples politely holding hands. The real quantum state is collective and subtle. Many electrons participate in a coherent state spread through the material. The key point is that superconductivity shows how quantum behavior can become visible on a large scale when many particles act together under the right conditions. This is one reason superconductors matter in quantum technology. Superconducting circuits can behave as artificial quantum systems, and they are used as one of the leading platforms for building qubits. In these circuits, electrical currents and electromagnetic fields can be controlled in ways that allow superposition, coupling, and entanglement. Companies and research groups working on quantum computing often use superconducting qubits cooled to temperatures close to absolute zero, because warmth is the enemy of delicate quantum control. Atoms and ions offer another major platform. Trapped ions are individual charged atoms held in place using electromagnetic fields. Their internal energy states can serve as qubits, and lasers can be used to control and entangle them. The National Institute of Standards and Technology has played a major role in trapped ion research, along with university laboratories around the world. The University of Innsbruck has also been strongly associated with trapped ion quantum experiments. Neutral atoms, which do not carry a net electric charge, can also be trapped and arranged using laser light. Researchers at Harvard University and elsewhere have used arrays of neutral atoms to explore quantum simulation and controlled many-body dynamics. These systems allow scientists to arrange atoms almost like carefully placed beads of light and matter, though the beads are quantum objects and the arranging requires rather more equipment than an ordinary craft table. Quantum dots provide another example. A quantum dot is a tiny semiconductor structure that can confine electrons or holes in a small region, giving it discrete energy levels somewhat like an artificial atom. Quantum dots can be used to study electron spin, photon emission, and possible qubit designs. Again, the larger idea is that entanglement is not restricted to free-flying particles of light. It can appear wherever quantum states can be prepared, coupled, and measured. This broader view also leads to quantum simulation. Richard Feynman famously pointed out that quantum systems are hard to simulate with ordinary classical computers because the amount of information needed can grow extremely quickly. One way around this is to use one controllable quantum system to imitate another quantum system. Trapped ions, neutral atoms, superconducting circuits, and other platforms can be arranged so that their behavior helps researchers study materials, magnetism, phase transitions, or models that would be too difficult to calculate directly. Entanglement is central to many of these efforts, because it is often part of what makes the simulated system genuinely quantum. If the particles in the simulator remained completely separable and independent, the simulation would miss the deep correlations that give many quantum materials their unusual behavior. Preserving and measuring entanglement helps scientists understand not only individual particles, but collective states of matter. So the strangest connection in the universe is not confined to pairs of light beams in a dark laboratory. It appears in matter. It appears in materials. It appears in the controlled stillness of trapped ions, the cold precision of superconducting circuits, the engineered smallness of quantum dots, and the dense complexity of condensed matter systems. It is not a decorative curiosity at the edge of physics. It is a recurring feature of the quantum world whenever nature is examined closely enough. The connection is strange, but it is not rare. It is woven into the behavior of matter itself, waiting beneath the surface of things that, from a distance, look perfectly ordinary. At first, empty space seems like the simplest place in the universe. Remove the planets, remove the stars, remove the dust, remove the air, remove every drifting atom and every wandering photon, and it is tempting to imagine that what remains is nothing. A clean blank, a silent gap, a cosmic room after everything has gone home for the evening. But modern physics has made empty space much harder to describe than that. In quantum field theory, particles are not usually treated as tiny isolated beads moving through an otherwise empty stage. Instead, particles are understood as excitations of underlying fields. An electron is connected with the electron field. A photon is connected with the electromagnetic field. Other particles belong to their own fields as well. These fields are not little objects sitting at one location. They extend throughout space, and particles appear as local disturbances or excitations within them. This changes the feeling of emptiness. A vacuum, in quantum field theory, is not simply a place where nothing exists. It is the lowest energy state of the fields. That phrase sounds peaceful, and in one sense it is. It is the most empty state a field can have. But it is not the same as absolute nothingness. The fields still have structure. They still obey quantum rules. They can still contain correlations, fluctuations, and possible excitations. Empty space is not crowded in the ordinary sense, but it is not a blank absence either. This is one of the reasons quantum field theory became such a powerful framework. It allowed physicists to describe particles and forces with extraordinary precision, especially in quantum electrodynamics, the quantum theory of light and electrically charged matter. Paul Dirac helped build the bridge between quantum mechanics and special relativity, and his work led to the prediction of antimatter. Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga developed powerful methods for quantum electrodynamics, while Freeman Dyson helped show how their approaches were connected and consistent. The theory became one of the most accurately tested in all of science. Yet beneath that success lies a quiet strangeness. If fields extend through space, and if their vacuum states still have quantum structure, then even regions that seem empty may not be completely independent of one another. Quantum field theory allows correlations between different regions of space. In some cases, those correlations can be understood as entanglement. This is a deeper version of the same theme that began with pairs of particles. Entanglement already challenged the idea that two separated particles must always have completely independent descriptions. Quantum field theory makes the challenge broader. It suggests that even when space is divided into regions, the quantum state of fields in one region may not be fully separable from the quantum state of fields in another. The fields can hold relationships across boundaries that are not visible as ordinary matter or radiation. This does not mean empty space is secretly sending messages. It does not mean regions of space are chatting to each other in a hidden, faster-than-light language. The distinction between correlation and communication still matters. Entanglement in quantum fields does not become a cosmic messaging service, and it does not break the rules of special relativity. But it does suggest that the idea of perfectly separate pieces of reality is, once again, too simple. One important concept here is entanglement entropy. In gentle terms, entanglement entropy is a way physicists describe how much quantum information is shared between parts of a system. If a system can be neatly split into two independent parts, the entanglement between them is low or absent. If the parts are deeply tied together in the quantum state, the entanglement entropy is larger. It gives physicists a mathematical measure of how strongly the description of one part depends on the description of another. In ordinary examples, this might describe two particles or a set of qubits, but in quantum field theory, the idea can be applied to regions of space. One can ask how much entanglement is associated with the fields inside one region compared with the fields outside it. The answer is often connected to the boundary between the regions. This has become especially important in studies of black holes, quantum gravity, and the relationship between space-time and information. Even the vacuum can contain entanglement across space. That idea is easy to say and difficult to fully absorb. The emptier state of a field may still contain correlations between what happens here and what could be measured there. It is not an empty box with nothing inside. It is more like the lowest possible hum of the quantum fields, too subtle to be pictured as ordinary stuff, but still rich enough to carry structure. This is where the title Strange Connection becomes even stranger. Quantum entanglement may not only join particles created in a laboratory, it may be part of the deeper fabric of fields throughout space. The same broad principle that makes two photons share a quantum state can also appear in the way quantum fields describe the vacuum itself. Separateness becomes less obvious, not just for particles, but for regions of space that once seemed empty and independent. Still, balance is important. Quantum field theory is extraordinarily successful, but the deeper interpretation of vacuum entanglement remains an active area of research. Physicists can calculate many effects with stunning accuracy, yet the full meaning of entanglement in fields, space-time, and gravity is still being explored. Some ideas are well established within quantum field theory. Others reach into speculative territory, especially when they touch the unresolved problem of uniting quantum mechanics with general relativity. So empty space should not be turned into fantasy. It is not a mystical ocean of limitless possibility where anything can be claimed without evidence. But it is also not the simple nothingness that common sense first imagines. It is the ground state of quantum fields, and those fields can possess structure even when no particles are present in the ordinary sense. The universe then becomes less like a collection of isolated things floating in a blank void, and more like a vast pattern of fields whose quieter states are still governed by quantum rules. The strangest connection in the universe may begin with pairs of particles, but it does not end there. It reaches toward the meaning of matter, vacuum, space, and the subtle relationships that remain even when almost everything else has been taken away. Quantum entanglement is one of the strangest confirmed connections in physics, not because it gives the universe a secret faster-than-light messaging system, but because it changes what separation itself seems to mean. Two particles can be far apart in space, and yet the most complete quantum description may still belong to the pair as a whole, not to one particle here and another particle there, each carrying a private little answer sheet, but to a shared quantum state that describes the combined system. That is the quiet shock at the centre of entanglement. It does not make distance vanish. It does not turn space into an illusion. But it does show that, at the quantum level, distance is not always the same thing as independence. The path to that idea has been careful and strange. Ordinary connections begin with contact, signals, shared histories, and hidden information. A pair of gloves in two boxes can explain ordinary correlation perfectly well. But entangled particles are not merely quantum gloves. Bell's theorem showed that broad classes of local hidden variable explanations must obey certain statistical limits, and Bell tests showed that nature can go beyond those limits. The results do not match the simple picture of particles carrying prewritten instructions from the moment they are created. That does not mean anything goes. Entanglement does not let anyone send messages faster than light. It does not allow distant particles to carry controllable commands across space. It does not overthrow Albert Einstein's special relativity as a communication rule. Each local measurement result still appears random, and the meaningful pattern only appears when observers later compare their records through ordinary communication. Nor does entanglement prove telepathy, mystical intention, or the idea that consciousness is required to create reality. In physics, measurement means a physical interaction that produces a record. A detector, an atom, a photon, a measuring device, or the surrounding environment can all be part of that process. The human mind is not needed to sprinkle reality into existence, which is probably a relief, given how often human minds forget why they walked into a room. What entanglement does reveal is subtler and more powerful. It shows that quantum systems can possess relationships that are not reducible to the separate properties of their parts. That idea reaches into modern quantum communication, where entanglement can help protect information. It reaches into quantum computing, where fragile shared states may become tools for processing information in new ways. It reaches into quantum field theory, where even empty space is not simply nothing, but the lowest energy state of fields that may still contain correlations. And at the edges of modern theory, it reaches toward black hole information, holography, and the possibility that entanglement may be connected to the deep structure of space-time itself. The universe, then, may be less separate than it looks. Not blurred, not magical, not lawless, but joined in ways ordinary intuition was never built to expect. Things that appear divided may still belong to deeper patterns of relationship, visible only when experiments are precise enough, mathematics is patient enough, and expectation becomes quiet enough to listen.